Oh, hey there. Thanks for coming out to lesson 10.4, which is algebraic solutions to single variable inequalities. And more specifically, we're looking at quadratic inequalities. We have, in a previous lesson, done a graphical solution method to see where a function is positive or an expression is positive or negative. And we know how to graph quadratics, so we can use that graphing method as a way to work with things. What we don't necessarily know how to graph yet, but will next year, are polynomial functions of higher degrees. These all have degree 2, because they're quadratic, but like a cubic or quartic or quintic function, those will have higher exponents, and next year you're going to have to be able to get some inequalities solved with them so you can tell where y is positive or negative, which does lead to graphing. So this year, we look at an analytical method for solving a single variable quadratic inequality. When we are solving those, we're going to find some things called critical values. Critical values are essentially the zeros of a function. The reason why they are critical is perhaps how they pertain to the x-intercepts of the graph. Because whenever you have a graph and it's got some x-intercepts somewhere, those are the points where you can cross from going negative land to positive land. And if you want to get back from positive land to negative land, you have to cross over that x-axis again. And so that idea that we could potentially go from positive to negative or negative to positive, that is tied to the existence of an x-intercept, at least when we're dealing with polynomial functions. So to figure out what's happening for the y values, whether they're positive or negative, we make something called a sign graph. And a sign graph is a diagram that shows the sign of an expression or a function or over its entire domain. So it'll tell us where the expression or where y or where f of x is positive and where it's negative. It'll also tell us where it's 0, and again, we're going to get that from the zeros of the functions, which match the x-intercepts of y equals f of x. So for us to get the zeros of a function like this, we're going to have to be able to factor. We can rewrite f of x as being x squared minus, whoopsie daisies. We're going to factor that. It's going to be the product of two binomials, and more specifically, it's x minus 5 times x plus 3. The zeros of this function are 5, I can write that better, 5 and negative 3. Those are the values of x that make the whole function value equal to 0. And because we're drawing a sign diagram, we're going to say that those are our critical values, or CVs for short. You don't necessarily need to write that down, but it can help frame your thinking. From here, we're going to start drawing the sign graph. And the sign graph is really an enhanced number line. Boom, there's a number line. And usually on a number line, you'll see all sorts of values. There might be a 0 and a 1, 2, and 3, and maybe negative 1, negative 2, negative 3 in the other direction. But we don't need to plot every single one of those. We're only going to plot the ones that are kind of critical importance to us, which would be these critical values. And of course, when we plot them, we're not going to plot them in whatever order we find them, but the order they would appear on a number line. So the least on the left and the greatest on the right. Those are the values of x we're dealing with. And for those values of x, certain things happen for f of x. Now we know that negative 3 and 5 are zeros of this function f of x. So right above that tick mark, we put some zeros. So when x is negative 3, f of x is 0. That's what that says. And when x is 5, f of x is 0. That's what that little area says. What we need to know will be the signs of these three regions we've partitioned this number line into. And each one, wondering, is it going to be something that's positive or something that's negative? There's a number of ways we can figure it out. One relates to our knowledge of quadratics. This is this graph, the graph of y equals f of x in this case, is going to be a parabola with two x-intercepts that specifically opens upward because of this positive leading coefficient. The only way you can have that happen is like this. So in your head brains, that's what you're thinking of. You're picturing that particular quadratic function. For that quadratic function, sometimes it's above the x-axis, sometimes it's below the x-axis. And we know that at -3 and 5, it is on the x-axis. So when we look at this first interval, when x is less than -3, when x is less than -3, remembering that -3 is this leftmost intercept, before that, all the y values are positive. So f of x in that interval is positive. Between these intercepts, we're looking at values of x that are between -3 and 5. And that's between those two intercepts. Between those two intercepts, the y values are all negative. So the sign of that region is negative. That's what this says. It says is when x is somewhere between -3 and 5, f of x is negative. And finally, how does one zoom out? Skills. When x is greater than 5, is this positive or negative? We look at this graph again, and we note that, well, there's 5, and to the right of it, y is positive. So f of x will be positive in that span. This is your sign graph, your sign diagram, however you want to phrase it. So this thing right here, it tells us what the signs of f of x are over the domain, over its domain. So when x takes on certain values, we can tell if f of x is going to be positive or negative. And we can get that from picturing the graph. But as I mentioned, there is another way. The graph is very handy because we are using quadratics a lot this year. It's a huge theme of the course. But there's another method that can be used that has applications with other polynomial functions. And that is using test values. So when we test values, we do look at the intervals we're dealing with, and we pick a random value of x in that interval. So this is everything before -3. Before -3, we could be talking about -4, -5, -10, -1,000, just any number that's in that area. Let's go with -10, just for funsies. Just anything in that region. When x is -10, x minus 5 is, well, -15, so that's negative. And when x is -10, x plus 3 is -7, that's also negative. And since f of x is the product of those two factors, f of x is a negative number times a negative number. And that negative number gets us something positive. So it's another way we can ensure that, yes, we are correct. It's because you got a negative times a negative in that region. When you're looking at the next region over, somewhere between -3 and 5, pick any random number. I like to work with 0 if I can. 0 is in that span. So when x is 0, x minus 5 is -5, so that's negative. And x plus 3 is 3, and that's positive. The product of those two is a negative times a positive, which is going to be negative. And that's why that region's negative. And we'll find a similar thing happens when we try to figure out what's happening in the last region. Something that's more than 5, you'll find it's overall positive in that same way. Anyways, that's a lot of talking. Yikes. Even I don't like to hear my own voice that much. Must be torture for you. So take some moments away from this voice. If you enjoy this voice, too bad. You can't listen to it right now. You have to try some examples. So try these other 3 examples on this page. See what you get for sign diagrams. And I don't know, did I say a time? I don't know. 5 minutes and 23 seconds. And then resume. Well, you know what they say? They say, might as well try example 10.4.b. It's a very common thing that people say. You might have factored this, and there's a couple ways you could factor it, but for me personally, I'm seeing a difference of squares, and I'm just going to say that it's 3 plus x times 3 minus x. I know conventionally we're used to seeing variable terms first and then constants, but it's still totally exactly what this represents. The critical values of this are positive 3 and negative 3. So on the sign diagram, I put those x values, and at those x values, oops, not f of x, almost got it, E3 variables error, how awkward, am I right? But g of x would be 0 at those parts. And you can either picture the graph of the parabola, or use the analysis by plugging in test values. But when we graph that, it's a sad face parabola. And so we know it's opening down because that negative leading coefficient, and it's got 2x intercepts. That's the only way for it to happen. Which means on the very left, it's negative. In between, it's positive. And on the very right, it's negative again. So this sign diagram will be negative, positive, negative. And if you got that, give yourself a way high five. Show whoever the adult in the room is right now what it's like when y'alls give yourselves a way high five. Wow, that was a great way high five. I hope you actually did it, because otherwise that comment's just weird. Well, next example. This thing factors as, well, that's just x plus 2 squared. Interesting. Where's the vertex of that thing? They say nobody knows. But you know. And the critical value here is just negative 2. So picturing a quadratic that has just one x-intercept, and it's opening upward with that positive lead. Again, you can picture it if you want, but x-intercept at negative 2, we're looking at something like that, where it is positive on the left, positive on the right. Pow, pow. That one is done. And let's get to the last one. Whoa, this one's intense. No worries, we have skills. I might personally take a couple extra steps, or maybe just one extra step for factoring. It is factorable without factoring out this negative leading coefficient, but I find it easier to deal with a leading coefficient that's positive. So factoring 2x squared plus 5x minus 3. I think it's like a 2x and a, let's zoom out of it here. And a positive 3, so minus 1. And x, I'm mostly certain that works. I don't know. That's 6x, that's negative 1x. We get 5x, all right. I'm calling it a win. So critical values here are 1/2 and negative 3. Sign diagram, where we check x versus h of x. In order, negative 3 goes first, and then 1/2. And those are both zeros of this function. You can picture the quadratic. We know this is opening downwards. So on the left and right, it's going to be negative, and in the middle, positive. So that's that business. Yeah, that's about that. On the next page, we're going to use these sign diagrams to actually solve inequalities. And when we solve those inequalities, we're going to be comparing the quadratic to 0 in some way. Is it greater than or less than 0? And we'll be noting that greater than 0 means we're talking about something positive. Less than 0 means something negative. And of course, if we're saying or equal to 0, That means we can include the 0 itself. Let's take a look. Woo! So solving this particular inequality, you want to find where x squared minus 3x minus 4 is less than 0. That means we want to find where x minus 4 times x plus 1 is less than 0. And that thing has critical values at 4 and negative 1. So we make a sign diagram. On the bottom, we'll have the values of x, which are negative 1 and 4. They are zeros of something. They're zeros of this expression. It's not f of x, unless you say let f of x equal all that stuff. But if you don't say that, if there's no f of x defined, you can't use f of x. That would be a communication error of not defining a variable properly. So we can just write it as x squared minus 3x minus 4. Picturing that, we're going to get something that's positive, negative, positive. That's the pattern it's going to follow. And solving that inequality, we are looking for where that expression is less than 0. Less than 0 means negative, and that's right here. So we know it's negative over the interval that goes from negative 1 to 4. Do we include the negative 1 and the 4? Let's check. This inequality is a strict inequality. So it's not inclusive. We cannot include the boundary points. So we use them round brackets. If you prefer more of, how you say, an inequality notation, we could also say that x is somewhere between negative 1 and 4. I'm personally a fan of interval notation, but to each their own. Follow your heart. Take a moment. Try the other three examples? Oh my gosh, there's 5. So try all the other examples. And, resume in, what's a good number? 7 minutes and 3 seconds. My, how time flies by. So you've already done all these examples, which is amazing. I'm 10 out of 10 proud of you. This thing factors as x minus 4 times x plus 2, which has some critical values that I'll place on my magical diagram. Negative 2 and 4. That's where this expression is equal to 0. The expression being, of course, x squared minus 2x minus 8. Noting again, this is an upward opening parabola. If I'm picturing it in my head brain, I'm saying this is plus minus plus. And the interval I want is where it is greater than or equal to 0. Greater than being positive, there's actually 2 separate chunks where that's happening. So x could be part of the chunk that goes all the way to negative infinity and then up to negative 2. Or it could be part of the chunk that goes from 4 all the way to positive infinity. Remembering that we always put round brackets on infinities because they're not numbers, they're ideas. Since this is an inclusive inequality, it's got the or equal to. We will include the negative 2 and include the 4. And to say that x could be part of either one of these, remember either one of these, we use a union symbol, which is kind of like a U. It's just not a U with a tail. Bad. But it is kind of like a Microsoft Word classifies it as a cup in its equation editor. But looks pretty much like a U. It stands for union, to say unite these two. And that's that. Well, on to the next one. Pew! This looks like negative x squared, plus 6x plus 9, which is the negative of x plus 3 squared, which gives me this sign diagram. Opening downward, I know the left and right sides are both negative. We want to find where this is less than 0. Oh, maybe I can just do the whole thing. But you can't do that. Nice try, because right here at -3, it's not negative. It's 0. 0 is not less than 0. 0 is equal to 0, and this is a strict inequality. So our valid answers here are everything from -infinity up to -3. Whoops, my 3 should look like a 3. And everything from -3 onward to positive infinity. You can also write this as x does not equal -3. Everything else is valid, just -3 is not. Example H. X plus 1 is less than or equal to 0. Man, I can't factor this. Like x plus 1, x plus 1. No, that's not what it is, because that's x squared plus 2x plus 1. That's not what we have here. In fact, x squared plus 1 is not factorable because it doesn't have any zeros. If you picture that thing, well, here's x squared, and then there's x squared plus 1. It has no x-intercepts, so x squared plus 1 has no zeros in itself. As a result, this thing is always positive. Where is it less than or equal to 0? Well, I don't see any negatives, I don't see any zeros, so that's a whole never. There is no solution to that. It's just madness. And it leaves us all in shock. Wait, you're right. Shock. Last two examples come down very similarly in terms of their factoring. Second last one is x plus 4 times x minus 3. And it's got a sign diagram. Looks like it's upward opening. We're looking at a plus minus plus situation. Where is it greater than 0? Well, that'll be over these two chunks. So that's everything from -infinity to -4, not inclusive, or everything from 3 to positive infinity. Similarly, this last one, if you factor out that leading negative, it's x squared plus x minus 12 left. Well, that's interesting because that seems to be what this expression was on example I. So this has the same critical values. Let's check out its sign diagram. These will be the signs of x squared minus x plus 12. Because that's downward opening, we go minus, plus, minus. What's rather interesting here is this seems to be the negative version we had in example I, but also the flipped inequality relative to example I, with, of course, like a little added or equal to there. And when we check out the solution for this one, it's those same two ends. Weird how that happens. I guess those are just life's little mysteries. In any case, solution, almost exactly the same. Except because this is an inclusive inequality, we can say that we use hard square brackets on those particular end boundary points. And that is solving quadratic inequalities in one variable analytically. The algebraic step was the factoring, in case you're wondering. Yeah. Suggested practice? I would try the worksheets. They are wicked awesome. So give them a go, give them a spin, give them a try, give them a whirl, give them a shot, give them a full-hearted attempt. And be good to yourselves, and be good to one another. I'm going to end this video now. Bye.